everybody. In this class, we shall discuss how to analyze a sequential logic circuit. Okay. So, this is the first discussion on this. So, we shall introduce the topic softly. So, we shall not take up very complex circuit. Okay. In future classes, we shall have discussion on more complex circuit. Okay. So, we have seen various representation of flip-flop in the previous class, and we shall make use of some of those representation in the analysis. Okay. So, we start with an example, and through solving this example, we shall learn the associated technique. Okay. So, the example that we have taken up, you can see, is a SR flip-flop based example, right. So, this is a SR flip-flop, this is another SR flip-flop. So, we have named it as A and B. Okay. So, input has been designated as SARA. Instead of Q and Q bar, we are writing A and A bar. Okay. So, that we understand that this is associated with flip-flop A, and similarly for flip-flop B. And what you see, the circuit has got other logic gates. This is what you are expected to see in a sequential logic circuit. It will be having combinatorial circuit elements, so called combinatorial circuit elements, that is basic gates, right, which does not have memory, and we shall also have these memory elements in the form of flip-flops. Okay. And later we shall see combination of flip-flops by which the registers will be part of the sequential logic circuit and other things. Okay. So, other building blocks we shall discuss later. Okay. So, there is some connection, right. So, you have to go through the analysis steps and figure out what this circuit as a whole does. Okay. And in doing it, since it is analysis, we shall make use of what you will see later, that truth table and characteristic equation. We are not looking into excitation table or state transition diagram in its analysis. Okay. So, that will be useful in synthesis part, which we shall take up later. Okay. Further, here we see that of course, this is a clock flip-flop, right. So, we consider that the clock cycle time, this is the way the clock is triggering, right. So, this clock cycle time is much more than the propagation delay of these basic gates. Okay. These propagation delays are of the order of nanosecond, 10 nanosecond or so. Okay. And in this flip-flop, of course, these frequencies could be in kilohertz, hertz or megahertz. Even in all those cases, this is not this delay is not comparable to whatever is the timing period. So, if the delay is comparable, what will happen? That again we shall take up later. Right now, in our first discussion on analysis of sequential logic circuit, we are considering a scenario where this propagation delay of basic gates is sufficiently small. Okay. And similarly, the circuit inside the basic gates that comprises of that goes into the making of these flip-flops. So, delay associated with them and delay of the flip-flop is also small. Okay. So, that is what we consider. Okay. So, first we look at representation of different inputs of the flip-flop in terms of the current state value, right. And in this particular circuit, there is no external input. So, if there was external input, we would have represented in the form of using that external input also. So, we shall take up example where there is external input in sometime later. Okay. So, and also we shall do it for the output, this final output that is getting generated here, right. So, we see what is happening for SA input. So, if you look at SA input, right, this is nothing but whatever you see here A, right. So, that A, the current state value is fed back okay, and presented as SA. Is it fine? You can figure it out. So, that is the analysis part, right. You have to look at the circuit diagram and from that you can figure it out. So, SA is AN bar, right. What about RA? So, this is what we have to see, all the inputs we have to see the logical connection, logical relation. So, RA you can see it is coming from over here. So, this is the path it is taking, right. So, RA is AN, this is fine. Now, you have to look at SB. So, this is SB, what we see? It is coming from a AND gate, right. So, this AND gate is, one input is A and the other input is B bar. So, that is AN and BN bar. So, that is SB. And what is RB? RB is, RB you can see is that fine. So, this is AN, this is one is there, another is, this is coming over here, that is BN, right. So, AN and BN, right. And also you can see the final output X is BN and AN, right. So, final output could have been taken from here also, if it is so possible, okay. Otherwise, if it is to drive something else and all, so it depends, right. So, but logical relation of both of them is same for this particular example. For some other example, it could be different, okay. If we, depending on the requirement, it could be N BN bar or N bar BN bar, some such thing or whatever, okay. Is it clear? Now, we have understood what is SA, RA, SB, RB and X, okay, how they are logically connected. So, that is the first step that we do in the analysis. So, next we come to something which looks formidable now to begin with, but once we go through the process, we will see that it is not that difficult to understand what is happening here, okay. So, it is called state analysis table or state table, okay. So, in this we begin with an initial state, okay. We are analyzing the circuit. So, so initial state, if not otherwise mentioned, so you can assume it to be 0, 0. That means the current value of the flip flop is 0 and 0. Is it okay? Okay. Otherwise, it will be mentioned that it is initialized with this. Clear? So, and how we can make sure that this is 0, 0? So, the flip flop usually will be having a asynchronous clear or clear input, okay. In some of the flip flops preset input may also be there, but clear is available, okay. Otherwise, also you can drive to the I mean, if it is so possible, okay, by synchronous clear or preset also you can come to a particular initial state, okay. So, it is fairly acceptable, reasonable to assume that the initial state is 0, 0 if it is not otherwise mentioned, okay. So, that is what we mean by clock 0, and then with clocking this circuit will move from one state to another and the corresponding output will get generated, and that is what we have to investigate. Is it okay? So, this is the current state, this is SBRB the inputs, SARA the inputs, these are the next state and this is the output. So, this is how the state table has been configured, which is understandable, right. So, if the current state is 0, 0 and we have already seen the equation for SBRB and SARA, okay. So, what is the current input? Okay. So, if it is 0, 0, both of them are 0, 0. For SB, you can see AN is 0, right. So, this is 0 because this is AND logic, and here also AN is there. So, both of them are 0. So, if both of them are 0 for flip flop B, what will be the, so this is flip flop B, what will be the next state? Okay. So, 0, 0 means previous value will be retained. So, Bn is 0. Is it clear? Right? So, that is what you would see. And when the if you look at SA and RA, okay, it is inverse of n, okay, n bar. So, n is 0, so SA becomes 1 and RA becomes n itself, so it is 0. So, 1 0, so it will get set. So, this is 0 1. Is it clear or not? The first row, only the first row. Okay, right. So, then first clock trigger comes. So, basically Bn plus 1 is clock trigger has happened. Okay. So, the value will become 0 and 1. The flip flop will move from 0 0 to 0 1. So, when it moves from 0 0 to 0 1, right. So, at the next clock cycle, inputs will get changed accordingly, because the inputs to all these things and even the output is a function of an, bn, and had there been an external input, so that is a function of that. Okay. So, here you are considering only the states, right. So, for that we have to come to the second row of the state table. Okay. So, after first clock cycle, first clock trigger has happened. So, we have come to 0 1, and that 0 1 becomes the current state, okay, through which the analysis process will continue, with which the analysis process will continue. So, if it is 0 1, okay. Now, again we shall look at what is happening to this SBRB for Bn and An being 0 1. So, SB is An Bn bar, right. An is now 1 and Bn is 0. So, Bn bar is 1. So, 1 and 1 ANDed is 1. And what about RB? RB is An Bn. So, Bn is 0. So, 1 and 0. So, this is giving you 1 and this is giving you 0. Okay. So, this is 0. So, 1 0 means then Bn plus 1 will become 1. This part is clear. What about An? What about SARA? Now, we look at SARA. This part we have seen. Okay. So, SARA is An bar and An. An is now 1. Okay. So, SA becomes N bar is 0. Sorry. SA becomes 0, right, because this is 1 and this is 1, right, because it is An. So, 0 1 means it will become 0. So, next state when the clock trigger comes, okay, becomes 1 0 after second clock trigger. So, this 1 0 becomes the current state, okay, and this 1 0, then again if you look at SBRB, this is An is 1 and Bn is 0. So, you will see that An is 0 making it 0 and Bn here also N is 0. So, it is 0 0. Okay. So, 0 0 means previous value will be returned. So, this is at 1. Okay. And what is happening to SARA? Because it was 0, it becomes N was 0. So, SA becomes 1 because it is inverted and this is 0. So, 1 0 means it becomes 1. So, current state becomes, the next state becomes 1 1, and with 1 1 at the input. Okay. So, you will see again if you follow this equation, 1 1 as at the input, An is 1 and Bn is 1. So, Bn is 1 means this is 0. So, 1 ANDed with 0. So, this is 0 and this is 1 ANDed with 1, this is 1. Okay. So, this is 0 1. Okay. So, that makes it 0, Bn plus 1, and your SBRB. So, that SARA. So, SARA is your this just inverse of it. So, An is SA is 0 and this is 1. So, that makes it 0. Okay. So, that is next state becomes 0 0. So, when it is 0 0, you come over here, you see this is the first row. So, same thing will come over here and it will keep repeating. And in each case, if you look at the output, output is A n B n. So, whenever the current value is 1 1, the output will be 1 1 at that time. Okay. For the rest of the cases, it is 0. Is it fine? Okay. So, this is the way the state table will evolve. Okay. So, how will you represent the analysis result? So, you can represent through pictorially through state transition diagram. So, in the state transition diagram, what we are showing here is that this is the current state and this is the output that is generated. Okay. So, 0 0 is the current state, okay, and output generated at that time is 0, okay, that we have seen in the table, right. So, next state is 0 1, that means when the clock trigger comes, right, and this is 0, 1 0 after that, then 0 0 and this is 1 1 and at that time output is 1. Next clock again it goes back to 0 0 and it keeps cycling around these 4 states. Okay. So, this is one way we can visualize what is happening in that circuit after analysis. The other one is a text description, okay, where we say the circuit generates an output 1 at every 4th clock cycle. That is what you can see when it reaches the state BA is equal to 1 1, because that is the way these flip flops were designated, and repeats the state transition 0 0 0 1 1 0 1 1. Okay. So, that is the way it continues. So, for analysis a circuit is given, you analyze and you come to a state transition diagram for a pictorial description of it, or a text description to English statement to clearly explain what that circuit does. Okay. That is the analysis result. Now, in the representation of the flip flop, we said that timing diagram is very useful, but we did not take up. Now, here we can see the how timing diagram comes into play. Okay. So, for which we consider that this is the clock and it is getting triggered at negative edge of the clock. Okay. So, whenever a negative edge comes, the circuit can trigger. Okay. I mean the flip flops can trigger, right. So, we start with initial state B and A 0 0, that is what we have considered, right. So, when B and A are 0 0, right, up to this time point, what are the values of SB and RB? SB was B A prime B, okay. So, this is 0, okay. This was AB, so this is 0, right, and SA and is A bar. So, this was 1 at that time and RA is 0. Is it fine? Okay. So, this is what we can see from the previous circuit. If you here it is AN BN prime, this is SB is AB prime. Okay. So, there is a mistake, we have to please look at it. Okay. So, right. So, then what happens at this point when the clock trigger comes? When the clock trigger comes at this point, okay. So, depending on the values that are presented. So, this is 0 and 0, right. So, the previous value was 0 for B, right. So, SBRB is 0 0, SBRB is 0 0. So, it will continue to become 0 0. So, it gets the trigger over here. Before that it is not supposed to change, that we discussed before when clocked circuit, is triggered circuit or gated circuit or so. Okay. So, even if the input changes, unless the clock trigger comes, it is not going to change. So, this continues to 0 0 0. Okay. How long it will continue? Till the next clock edge comes. Okay. At that time it is suppose it can make a change if depending on the excitation, right. And what happens to A? A is 1 and 0. So, when the clock trigger comes, A becomes from 0 it goes to 1. Now, here what I was telling that we can show the delay if it is appreciable, which other representations cannot show. If the delay over here, flip-flop delay is comparable to this these clock period, sorry, from here to here, this is 1 clock period, from here to here this is 1 clock period, then we can show the delay, right. Here A is changing, we can show it like this, okay. That proportionate delay, that it has become 1, but after some time. And if the delay is cumulative or this delay is something by which the circuit can malfunction or can give some undesirable result, okay, that is better manifested through timing diagram based representation, but not by others. Okay. This is the usefulness of timing diagram based representation, and we shall see such cases in future when we study other sequential logic circuit. Clear? So, coming back, so 0 B continues with 0 0 and A becomes 0 to 1. Is it fine? Right? And it will remain 0 to like this till the next clock edge comes, negative edge triggered. Okay. So, when it is at 0 and 1, what happens to the inputs now? Okay. So, again this is A, B bar. Okay. Right. So, this becomes SB becomes AB bar. So, this becomes 1. Okay. RB is AB. So, this is 0. SA is A bar. So, this is A is 1. So, this becomes 0 and RA is 0. RA is 1 because it is A is 1 now. Is it fine? So, it is moving with the clock, right, synchronous with the clock, and it becomes 1. After that, that causes the changes in SB, RB, SA and RA. So, some small propagation delay will be there, right, but again this is okay, negligible compared to the clock period, because this logic operation, as I said, if it is appreciable, then we can show that SB is becoming, after this has changed, okay, like this, then from that it will further small delay and it will be shown in that manner. Okay. Otherwise, we are neglecting that part. Okay. So, 0, 1, so this is 1, this is 0, this is 0 and 1. Now, clock trigger negative edge comes. Okay. So, at that time again circuit can change. Okay. Again let me correct every time. Okay. So, this is okay. So, then what happens? 1 0. So, sorry, SB is 1 0. So, B becomes 1, right, and SA is 1 0, right. So, SA is 0 1 SA RA. So, it becomes 0. So, from 0 0 it goes to 0 1, then 1 0, and then you can see that it goes to 1 1 and then again it repeats at 0 0. Okay. So, this is the way the timing diagram can be used to show how the circuit moves. I mean, that is through the analysis process, and each time you can show the output over here and based on the current input, and when both the inputs are 1 1, right, you can show the output is coming 1 1 just after a small propagation delay, if propagation delay is comparable. Fine, right. So, we can use characteristic equation also directly, since we already are familiar with characteristic equation, right, to come up with the analysis result. Okay. So, we have seen that SA and RA, how it gets represented, and we know the flip-flop equation of SR flip-flop. So, AN plus 1, we can write it in this manner, SA plus RA prime AN. right. And when we substitute SA from here and RA from there, and we just simplify, we see that an plus is an bar, n prime, okay. And that we had actually seen in the previous cases, in the timing diagram also, that it is just toggling. Output is A flip flop is simply toggling in every clock cycle, okay, and that we can see from the equation also. Similarly, SB and RB we have seen, right, and we have got flip flop equation. Now, instead of Qn plus 1, we are writing Bn plus 1, Qn we are writing Bn, and if we substitute and norm and put it into a more compact form by going through the steps of minimization, so we see An XOR Bn. Okay, we can have the state table. So we can where this is the current state, again as I said, if it is not specified, we can begin with this current state, right, and then we can look at this equation. So Bn plus 1 is A XOR Bn, right, A XOR Bn is 0 0, so it is 0, and what is An plus 1? It is just inverse of it, so this is 1. So 0 1 becomes the next state. So 0 1, this XOR, this becomes 1, and An prime, so it will become just the opposite of it, that we already know, we have seen from this equation. Then becomes 1 0 becomes the current state, XOR is 1, and An it just gets complemented, so this is 1, so 1 1 becomes the next state. So 1 1, right, XOR 1 1 is 0 only, and then 1 toggles becomes 0, so next state becomes 0 0. So 0 0, again you come back to the looping of it, cycling of it, so it is 0 1 and it continues this way, right. And when it is current state is 1 1, we can see that output is An Bn, so which is 1, fine. Finally, we look at one again simple example for the first class on analysis of the circuit, okay, where there is an external input present, okay. So here is a D flip flop clock, and then there is an external input, right, and there is a output that is getting generated in this manner. So first step is what? Getting the equation at the input of the for the input of the flip flop. So only one flip flop is used. So D is XOR X XOR Qn, that we can see this is Qn is fed back, right, and X XOR Qn. And what is Y? Output is X ANDed with Qn prime. Very simple. Is it okay? Now, if we just go by the state table method, we can go by any other method, okay. So state table method, then we can see the current state we assume to be 0, if not otherwise specified as I said, okay. And if input could be now either 0 or 1, because it is coming from outside, we do not know for sure. So if the input is 0, okay, then 0 XOR 0 is 0, right, which will make D flip flop, whatever is the input, that will go as the output, so this makes it 0, okay. But if input was 1, 0 XOR 1 is 1, next value would have been 1, okay. And at that time, since X Qn bar is the final output, so this is X 1 and Qn bar is 1, so at that time the output is 1. Now if the state is 1, right, and you receive a 0, okay, so 1 XOR 0 is 1 at the flip flop input, and then the output will become 1, right. And instead of 0, if you receive a 1, then 1 1 XOR is 0, right, output will be 0. So this is how this circuit works. So this circuit, every time from current state to go to the next state, it looks at the input, and based on the input, okay, and of course the current state, it moves to the next state and generates output, right. So for this we are looking at a state diagram representation as the analysis result, where the state is only one state, okay, so 0, and output is generated based on the input, directly from the input, okay. So for this we are showing output not inside the state. Earlier the output was generated solely by the state. Okay. So, we showed it inside the state. Here for input when it is 0, right, and the current, so this is now 0, right, and the current input is 1. State change will take place in the next clock trigger at the next negative edge. But when this is happening, right, the output is getting generated in this same cycle, clock cycle itself. So, that shows, that is shown in the state diagram side by side with the input. So, this is input and this is output. This is the convention. More about this kind of representation modeling we shall discuss elaborately later. Okay. So, 0 is present, 0 is the current state, input is 0, it will remain at 0, the next value will be 0, okay, output is 0. 1, output is 1, this goes to 1, okay. And then if it is 0, right, it will, when it is at 1, it remains at 1, output is 0, and when it is at 1, it goes to 0 and output is 0. So, what you can see, if you now look at this state diagram, this particular circuit, except if you ignore this output y, rest of the thing which is there in this box is nothing but your T flip-flop, isn't it? So, in the T flip-flop state transition diagram if you had seen, so this part was not there, okay, this part was not there, rest of the things are same, okay. So, we analyze this circuit and we see that this is how the circuit will behave, and this is the corresponding text description that it toggles when the input is 1, right, and maintains otherwise maintains previous state, and output is 1 when output is 1 when input received at state 0 is 1, else output is 0. So, that is the analysis result. Okay. So, to conclude, analysis of sequential logic circuit begins with specified assumed initial state. Commutatorial circuit logic part is analyzed to find out the relationship at flip-flop terminals, logic relationship and for the output. In the state analysis table, all inputs of the flip-flop at a given state is described, and next state is obtained, and that serves as the input for current state for the next row of the table. Okay. And it can be presented through state diagram, final result, or a text description. And timing diagram based analysis is useful to evaluate the progress of the state, and it can show the effect of propagation delay. When it is comparable, it is very much required and useful. And flip-flop characteristic equation can also be used for analyzing the circuit, okay, and for which some algebraic manipulation is required. Okay. Thank you.